can you hear me now?
Yeah, I can.
Okay, so this means my earphone is not working. So last week at 3 p.m. actually I uploaded to YouTube. So were you able to access that? Hello? Hello?
Hello.
I hope my voice is audible. Actually, my earphone is not working, so I am using the direct audio of my laptop. So just please let me know if it is audible or not. Hello?
Hello.
Were you able to hear what I just said?
No, I was. I just went on your YouTube link. So it was just open.
Okay, I was saying that am I audible?
Yeah, now you are.
There seems to be some So it is
Hello.
it is okay, right? So I can start.
Yeah. Yeah. Please.
Okay, okay. So I hope my screen is also visible. You can just write one yes in the chat box if that my screen is visible. Now, okay, so I am starting then. Because the screen is not visible. I don't know why, but there seems to be some problem today. Okay, okay, thank you. Okay, so welcome to this course of chemical crystallography. So this is we are towards the almost end of this course. So if you have any questions, so please ask your questions in this Ask a Question tab in this of this SWAM portal. So the professor, so when he will see it or when the TA sees it, so they will try to answer your questions. So please ask whatever questions you have from whatever part. And if you want to know anything extra and also and if you want to have any extra lesson or this kind of live session about any particular topic, so you can post that in this in that Ask a Question tab. So if you are have if you want to learn about any particular part, so you can write that in that mail also in that Ask a Question tab, and then all of us will get that via mail. Okay. So this is the week 11. And welcome to this live session number 11 of this course. So today, last week, please watch the video on YouTube if you have not watched it yet. So last week we have discussed about assignment 8. So as far I could see, so you have assignment 9 and assignment 10, which was supposed to be completed before today. So I today I will discuss about assignment 10 and then assignment 9. So assignment 9 is is that week 9, comprising of assignment 9 is a very important topic about the Lorentz factors, the polarization factors, and also this absorption correction. So the absorption corrections and also they are not only theoretical things but they are very much important if, practically when solving a crystal structure. That is why we will be talking about that assignment in the next. Hello. So welcome to this session. Let me share my screen. So, welcome to this course of chemical crystallography. So, today's the today's technically the 12th week or the 12th session. But in the last session, there was a issue of this of network from my end. So the candidates were not able to hear. Uh, we did not continue that session. So today is technically the session 11, and for session 12 I will record and upload and also share the link. The till now the assignment till up to assignment 8 has been covered. So since we are now towards the end, so today we will cover two assignments, that is assignment 9 and assignment 10, and the contents we will discuss for 2 weeks. And in the next session, which will be the last session, there I will talk about the powder X-ray refraction or PXRD, which was covered by the professor in week in the last 2 weeks, and also we will cover the last two assignments in the next week. So for today we will talk about some things. So about when now we are towards the end, so we are in the structure solution and refinement and direct method, Patterson methods and everything. So before let me go into the topic. So we have these corrections, right? The absorption correction and then the Lorentz factor and the polarization corrections and everything. So we will talk about that. We will talk about the concepts first and then we will proceed towards the uh, assignments, right? So Lorentz factor arises from the time which is required for a reciprocal lattice point to pass through the Ewald sphere. So by now, I hope all of you are, well versed with this concept of reciprocal lattice points, the Ewald sphere, and everything in the reciprocal space. So during data collection, what happens is the crystal is moved, right, moved by an angle. So when it is moved on its axis, it is this angle phi. So when it is moved, then there is a time required for a reciprocal lattice point to pass through the Ewald sphere. So why that happens? This happens because of two things. Firstly, when we consider the Ewald sphere, it is not just like a single line, so it has a definite space, and also a reciprocal lattice point is not an infinite, really small point. So it also has a certain kind of volume associated with it. So it there is time required for the reciprocal lattice point to pass through the evosphere, and that time is not constant for all the reciprocal lattice points, because the reciprocal lattice points are spread over a region, and depending on where the reciprocal lattice point is and the angular velocity associated with that, so based on that, the amount of time which is required for the point to pass through the evosphere will be different for different reciprocal lattice points. So if we consider that the crystal is rotated by an angular velocity of omega, then the reciprocal, if the crystal is rotated at a given angular velocity, then along with the crystal, the reciprocal lattice will also rotate at the same angular velocity, right? However, the linear velocity associated with the reciprocal lattice point will be different. So the relation between the linear velocity of a reciprocal lattice point and the angular velocity is related by this d star. So this is the Lorentz factor. Then we have this identification from intensity statistics, the presence of inversion center. That is whether or not we can argue that an inversion center is present or not in the crystal lattice from the intensity statistics. So if what happens in general for all the light atom structures, Friedel's law is held. That is intensity of HKL is equal to intensity of H bar K bar L bar. Right. So Friedel's law is held for both centrosymmetric and non-centrosymmetric structures, but for structures which contain heavy atoms, so they tend to show some deviation from the Friedel's law to some extent. So careful observation of the intensities can indicate the presence or absence of inversion center in a crystal structure, which is called as the Z test or the NZ test. So in 1949, Wilson showed that the probability distribution of intensities of X-ray reflections from the crystals are different for centrosymmetric and non-centrosymmetric crystals. So the details of it you can obviously get from the the video by going through the class of the professor. So going through the class of the professor. So if you plot the Z test, then if it is a straight line, then it is non-centrosymmetric, and if it follows a curve like this will be centrosymmetric. Then we have the Wilson plot to identify a good data set from a bad data set. So I want to emphasize here that all this you can go through the videos in detail. So I am just here touching upon the topic so that it will help me to explain the assignments, right? So to go into the details, you have to go through the video. In the videos, they are beautifully explained, and you will be able to understand everything very easily. Okay. So this is the Wilson plot where we have a straight line which has a particular intercept and a particular slope, where the slope is minus 2b. So this was the question asked in the assignment. That is why I am presenting it here. That what is usually the slope of a Wilson plot? The slope of a Wilson plot is minus 2b. So I hope all of you have answered it in during the assignment, right? So now we come to the questions. Okay. So in the questions, so the first question. So these are the questions from assignment 9. Okay. So the first question is that the linear velocity of reciprocal lattice points is equal to the angular velocity of rotation of crystal along its own axis. So we have learned that the linear velocity and angular velocity is not related. The linear velocity and angular velocity is not equal. It is related by d star, reciprocal lattice unit. So it will be false. Then the second one is that Lorentz correction is applied to all the reciprocal lattice points which are responsible for X-ray diffraction. This is true. Then thermal vibrations vary inversely with the mass of the atom. So if we compare hydrogen, carbon and lead, so we are progressively increasing the mass. So hydrogen to carbon to lead. So you cannot even fix the position of hydrogen from X-ray diffraction, right? Because it is so light. But you can fix the position of carbon, and you can definitely fix the position of lead. Why? Because thermal vibrations decrease if the heavier the atom is, the less it will fluctuate. So this will be true. Then this question, we can indicate if inversion center is present in the lattice or not from careful observation of IH scale. This is from Z test, so it is true. So this was a kind of mathematics question. So I hope you have enjoyed solving it. So the question was that if we have a system, any crystal system, so here it is written NaCl, where the d spacing is given for a particular H scale, that D11 is equal to 3.255 angstrom. Then what will be the polarization factor for the 111 reflections if copper X-ray is used? So what do we have to do? First, we have to know the formula of the polarization factor. So polarization factor is equal to half into 1 plus cos square 2 theta. So now we simply have to find out cos square 2 theta. So for that, the most necessary thing is that we have to find out 2 theta, right? So we know Bragg's law, we know n lambda is equal to 2d sine theta. So if d is given, that is 3.255, we can substitute 2 into this d. 3.255 into sine theta will be equal to n lambda. So n is usually taken as 1, lambda will be 1.54, because in the question it is given that copper X-ray is used. So then we can calculate sine theta from here, then we can calculate theta, and if we multiply by 2 we can calculate 2 theta. So I hope my recording is going on. Okay. So if we have 2 theta, then from there we can find out cos 2 theta and then cos square 2 theta. Then if we just substitute that the values in the formula of polarization factor along 111, 1 plus cos square 2 theta by 2, we will get this cos square 2 theta is 0.789, then 1 plus cos square 2 theta will be 1.789 divided by 2 will be 0.894. So if we convert this into percentage, it will become 89%, approximately 89%, right? So the other options were 69, 79 and 99. So none of them are close, so the correct option will be 89%. So which of the following statements is not true? The direction of polarization of an X-ray photon can change as a result of diffraction. So this is obviously true. X-rays are absorbed as they pass through the material according to Beer-Lambert's law. So this is true that IH scale, it depends upon the wavelength and the length and all that. So Beer-Lambert's law is held. So it's true. As the temperature rises, the atoms execute decreased excursions from their average positions. This is false, because if temperature rises, then the general movement, the vibration will be more, not less. And the last statement was that Lorentz factor arises from the time required for a reciprocal lattice point to pass through the Ewald sphere, which is again true. Hence, the option which is not true, the correct option is option 3 in this case. Then what is the slope of a Wilson plot? So Wilson plot is minus 2b, as we have seen before. Now systematic absences. So we have learned a lot about systematic absences in the previous classes, right? So systematic absences arise from what? It arises from the translational components, right, or lattice centering. So two factors are there for systematic absences. You should always remember it. Always. Systematic absences arise from lattice centering or translational components. So the screw axis means rotation followed by translation. Glide plane means reflection followed by translation. So glides and screws give rise to systematic absences along with centering. Hence, mirror planes or normal simple reflection planes will not give rise to systematic absences. Which among the following cannot be improved? Once the data has been collected is R int and R sigma. So this is also a very easy question. So this ends our assignment 9. So now next we will move to assignment 10. So when we move to assignment 10, so before that we need to discuss certain concepts. Some very interesting concepts are there related to solving the crystal structure or the structure solution and refinement. So when we want to solve a crystal structure, then what is happening? So we have a crystal, so it is diffracting and we collect a complete 3D set of diffraction data. Now the question is that whether this diffraction data has all the information which is necessary to completely determine the structure or the internal or underlying structure of the crystal. So can we use the diffraction pattern to locate all the atoms in the unit cell, that what are the exact positions of all the atoms in the unit cell? So can we use the diffraction pattern to get that complete information? So the answer, at least in most cases, is yes. So this is despite the fact that phase information is not available. So why so? Because of the fact that we can go to higher resolution to get better data. So we will learn that. Two methods are commonly used to get. Now if there is a phase information loss and we are not able to solve the structure without phase information, then two methods are commonly used. First is to use the so-called Patterson map, the Patterson method, and the second is the direct methods, which is like a kind of more widely used nowadays. So what happens in case of direct methods? So in case of direct methods, a few strong IH scales are chosen and their phases are assigned at random.